Hello, and welcome back to the course on University Physics 3. This is now the last lesson for Chapter 9. So before we proceed, let us first review some concepts. So in the previous lesson, we discussed about Faraday's law, which gives you the induced EMF for due to a changing magnetic flux. And in the previous chapters, we have discussed the relationship between the potential difference and the electric field. So actually related by this integral here, E dot dl will give you VAB, the potential difference between point A and point B, VA minus VB. For this lesson, we will be talking about induced electric fields. So because of a changing magnetic flux, aside from the induced electric field, which induces a current, induces an EMF, there's also, or the reason for the induced current is actually the induced electric field. So it's a non-electrostatic field, or it's an electrodynamic field. So the induced electric field is the electric field induced by the changing magnetic flux, and this is the responsible for the induced current flow. So it's a non-electrostatic field, so it's an electrodynamic field. So the EMF is actually just equal to the potential difference, and in this case, it's the closed integral of E dot dl. So sorry, it's not potential difference because it's a closed integral. So it's closed integral of E dot dr, and it's equal to the EMF, the Faraday's law that we have before. So if you have, for instance, a coil of wire, and the current in the wire is changing, for example, it's increasing. So if you place another loop, then there will be an induced electric field in the loop. That induced electric field is responsible for current flow, for the induced current in the loop. So in this case, this is just a cross-sectional view. So this is actually the current in the coils here. This is our blue cylinder. So the current is in this direction. And if the current is increasing, then the electric field, or the induced current and the induced electric field, will actually be in the opposite direction. So the induced magnetic field in this direction is, in this case, having a counterclockwise direction for induced electric field and induced current, such as to oppose the increase of the effect. But in the event that this current is decreasing, then the direction of the induced electric field will be in the same direction, and also the direction of the induced current. So again, nature doesn't want any changes in magnetic flux. It doesn't want any changes in current. So if the current is changing in this direction, then if it's increasing, then there will be an opposite induced current. If it's decreasing in that direction, then there will be an induced current in the same direction to oppose the change of current. So a practical application of this is the way how we measure alternating current. So this is a wire that's usual in our homes carrying AC for alternating current. Since the current here is alternating, so meaning it's changing, then this will induce a current in this clamp here, or in this loop here, and that can be read by your voltmeter or multimeter. So in this case, it's reading voltage, alternating voltage. It's 228 volts alternating current AC, 220 volts AC. So that's how we measure. That's one practical application of induced current and induced EMF, and induced electric fields. So there are many applications of induced EMF, induced current, and induced electric field. So you have the computer hard disks, the alternator in your car, and the rotating crankshaft of an airplane. So in this example, even if this rotating crankshaft of the engine keeps running, even if the airplane's electrical systems fail. So as an example for induced electric field, suppose in the figure, a long solenoid, so this is our solenoid, the black wires, has 500 turns per meter and a cross-sectional area of 4 centimeters squared. The current in its windings is increasing. So it's increasing at a rate of 100 amperes per second. So every second, the current increases by 100 amperes. It's actually a very large current. It's actually very dangerous levels of current. So 100 if it starts from 0, then after 1 second it will be 100 amperes. After another second it will be 200, 300. So it's increasing by 100 amperes per second. So find the magnitude of the induced EMF in the wire loop outside the solenoid. So in this loop here, the yellow loop, and find the magnitude of the induced electric field within the loop if its radius is 2 centimeters. Okay. So for letter A, we are trying to find the induced EMF. So we start with Faraday's law. Our flux here will just be B times A, since the magnetic field and the area vector are in the same direction. So the area vector is also in that direction. So since the current is the one changing, and you have obtained before when you solve the solenoid example, that the magnetic field of a solenoid, the magnitude is mu naught n times I. So n is actually the number density, number of turns per unit length. So how many turns per unit length? So it's actually given 500 turns per meter. So that's our n, number per unit length, number of turns per unit length. So therefore, our magnetic flux will be equal to, so B is equal to this one, so mu naught N I A. And the one changing is actually I, the current. So in this case, you have N is just equal to 1. So you can take out mu naught N and A out of the differentiation. So you have mu naught N A, and you're left with dI dt. So we are given all of these values. Mu is just a constant. N is 500 turns per meter. The area is 4 centimeters squared. You need to convert that into meters squared by multiplying 10 divided by 10,000 or 10 to the negative 4. And dI dt is actually given 100 amperes per second. So substituting all of those values, we will get negative 25 microvolts. Negative 2.5 times 10 to the negative 5 volts, or negative 25 times 10 to the negative 6 volts, or microvolts. Micro means times 10 to the negative 6. Okay. The negative sign here implies that the direction of the induced current is opposite of the direction of the current in the first coil. So the negative sign here implies that the direction is opposite of the direction of the original current, or the current in the first coil. Okay, so the magnitude of this is obviously 25 microvolts. Okay, so for letter B, find the magnitude of the induced electric field in the loop, within the loop, if its radius is 2 centimeters. So this is letter A. So for letter B, we are now trying to find the electric field. So the EMF is just the closed integral of E dot dl. So dl is this length, the length around the loop. So the total length of the loop is actually, if this is a circle, it's 2 pi r, the circumference of that circle. So we already know the EMF. So we'll only get the magnitude. So this will become, so the electric field at all points in the loop is actually the same. It's constant. So you can take it out of the integral. So it just becomes EDL. And the electric field and DL are in the same direction. So if this is the direction of DL, and that is also the direction of your electric field. So they are parallel. So E dot DL is just EDL. So you have E, integral of DL is just the total length of your wire, or sorry, the loop. In this case, it's 2 pi r. So we are given the radius of the loop is 2 centimeters. So this is now the magnitude. We are only talking about the magnitude. The magnitude of the electric field will now be the magnitude of the EMF over 2 pi times. And this will give you a value of 2 times 10 to the negative 4 volt per meter. Or volt, the unit volt per meter is actually equivalent to Newton per coulomb. So that's it. So moving on to another topic. So these topics are actually now optional. So you may or you may not view these topics. So eddy currents. So these are the currents that circulate in a conducting material, so conductor, metal, that moves through an external magnetic field. So if you have a metal disc rotating through a magnetic field, so for example, as a CD or DVD, then this will cause swirling currents called eddy currents. So eddy currents are swirling currents, just like swirls in rivers. So we usually call that in the local languages lilo. Okay, but in America, in the US American language, it's called eddies. Swirling eddies or eddy currents. That's why it's called eddy currents. So there will be eddy currents swirling around your conductor, your metal, if you expose it and the metal moves with respect to the magnetic field. So one application of this is metal detectors in airports, or the usual metal detectors used by the security guards or the treasure hunters. So in a metal detector in an airport, for instance, there's actually a transmitting coil and a receiver. So if there's no metal in between, the magnetic field is just constant. But if there's metal in between these two coils, there will be eddy currents in the surface of that metal, and therefore there will be an induced current in the receiver coil, and that will result in an alarm. So the detector will alarm. So in the same manner for metal detectors, so if there are swirling eddies, there are metals present under the soil or under the ground, then there will be eddy currents, and these eddy currents will further induce an EMF. So the electromagnetic induction is actually mutual. So we will discuss about mutual induction in the next chapter. So another optional topic is about the displacement current. So this is the fictitious current that flows to the plates of a capacitor. So take note, the plates of a capacitor, between that is actually an insulator, a dielectric. So how does current flow to a capacitor? So actually current doesn't flow actually between the plates of a capacitor. That's why there's the word fictitious. But it theoretically it fixes Ampere's law. So the displacement current is actually the change in electric flux. So this is E dot dA, the change in electric flux. The change in electric flux between the plates of the capacitor. So therefore, the generalized Ampere's law will now be the original Ampere's law is mu naught B dot dL is equal to mu naught I enclosed. But it's now the conduction current, the current that flows through the wire, plus the displacement current enclosed. So we now have a complete picture of the theory for electromagnetism. So we have discussed first this equation. This is actually Gauss' law. This is also Gauss law for magnetism. This is Ampere's law, and this is Faraday's law. So these four equations are collectively known as Maxwell's equations for electromagnetism. So even though these laws are not named after Maxwell, but Maxwell is the one who collected them all and to make a theory, a comprehensive theory for electromagnetism. So this is Gauss law for electric field or electricity, Gauss law for magnetism. Take note that for the Gauss law for magnetism, B dot dA, this is actually flux. This is also flux, electric flux, magnetic flux. So the total electric flux is just equal to Q, the charge enclosed, over epsilon naught. But the total magnetic flux is always zero, because for magnetism, it's a magnet is always a dipole. So that is where the symmetry between electricity and magnetism fails with respect to the existence of magnetic monopoles. You cannot see, or you cannot observe a single north pole magnet or a single south pole magnet. It's always a pair of north and south. Unlike electricity, you can observe a single positive charge and a single negative charge, but you can't observe that in magnetism yet. So people are actually still trying to find experimental evidence of magnetic monopoles, because there is nothing wrong if magnetic monopoles exist, if a single north pole or a single south pole exists. So this is the generalized Ampere's law, the conduction current, and the displacement current, and lastly Faraday's law. So these four laws actually describe the fundamental theory for electromagnetism. But actually these laws are still not the complete Maxwell's equation. This is only for electrostatics and magnetostatics. So that one. So another experimental feature of electromagnetic induction, induced EMF, or induced current, is what we call superconductivity. So in superconductivity, it is beautifully described by the phenomenon called Meissner effect, where there is an expulsion, or there's no magnetic flux or magnetic field inside a superconductor. So the magnetic field becomes zero inside the superconductor when exposed to an external magnetic field. So this happens at a critical temperature, Tc. So if you lower the temperature of a superconductor, of a normal conductor, there comes a certain temperature which is called the critical temperature, wherein it becomes superconducting. So when it comes to a superconductor, it has no resistance. It has no electrical resistance R. So it can basically accommodate all of the current that flows through it. And another one is Meissner effect. So the black slab here, this is the superconductor, and the circular thing here is the magnet. So a superconductor is a diamagnet. So it will exert a repulsive force on the magnet. So that is why it will support the magnet in mid-air. So in this case, the force due to repulsion, which is upward, and the force due to gravity actually balances. That is why it's floating. It's floating there. Okay. So if you have a normal conductor, not in a superconducting phase, then if you immerse it in a uniform magnetic field, then there will be a magnetic field inside your conductor. But if you have a superconductor, the magnetic field inside actually becomes zero. There's no magnetic field inside. So it's as if the electric field lines are evading the superconductor. And once you suddenly turn off the magnetic field, so supposedly there's a flux because you change the magnetic field from an initial value to zero, but still the superconductor is unaffected. So there's no change in magnetic flux in the material. So there's no induced current, induced magnetic field inside your superconductor due to the changing magnetic flux. That's one example of application of electromagnetism. So that's it for this lesson and for this chapter. So for the next chapter, we will be focusing more on mutual induction, and we will discuss the last basic circuit element. So we already have discussed the resistor, we already have discussed the capacitor, and we will be discussing the last circuit element, which is called the inductor. So I will see you again in the next chapter.